Welcome. We're going to talk about the second half of our discussion around data. We're going to start right in on what an influence diagram is. And this is often in developing a decision model or a function or equation. Particularly early on, it's helpful to create what's called an influence diagram, where you kind of say, well, my variable cost per unit times my quantity, that gives me my variable cost, and my fixed plus my variable add up to my total cost. And you kind of diagram it out, and that helps you actually come up with what the equation or the function or the model is going to look like. And there's some basic linear models like total cost equals fixed cost plus variable, and the variable cost or my variable cost per unit times my unit production. For here, I'm going to assume units produced and units sold are equal to each other. Break even is another one where revenue equals total cost. So revenue is my price per unit times the number of units sold. My total cost is my fixed cost plus variable cost. And of course, my variable cost I can break into variable costs per unit times units produced or units sold. So I could come up with the break-even volume by setting my revenue, i.e. price plus unit times units sold, equal to fixed cost plus variable cost per unit times units produced. And if we did an example, if the sales price was 10, cost per unit is 5, fixed cost 200, we could let x equal the number of units sold. So 10x equals our revenue. 5 times x plus 200 equals our cost. And by setting those equal to 0 and solving for x, we find that the break-even number of units is 40. Let's talk a little bit about uncertainty and risk that are in models. So uncertainty is the imperfect knowledge, and the risk is the consequences. So kind of the difference, if a plane was leaving today at 10 a.m., whether it's not on time or on time, there's certain uncertainty as to whether it's going to be on time or not. There's kind of always uncertainty in that airline business. But there's only risk to me if I'm traveling on that plane. If I'm not traveling on that plane, there's no consequences to me whether it's on time or not. So uncertainty is the imperfect knowledge, and the risk is kind of the consequences. So you can have uncertainty without risk. Models you can use to predict. The key advantage of having a model is you can predict things, called a predictive model. As with any math model, but they could be linear, a straight line, or nonlinear, a curved line. Here's an example of a linear predictive model. In economics, oftentimes you talk about quantity demand as a function of price, and it's negatively impacted. As the price goes up, the quantity demanded tends to go down. So we could say a function is 200 minus 0.25 times the price. An example of a nonlinear model might be compound interest, where you have principal times 1 plus the annual rate divided by the number of times compounded raised to the number of times compounded times t, the number of years. If you're not familiar with this, in simple language, nonlinear functions have exponents other than 1. Linear have a exponent that usually isn't shown because it's an exponent of 1. Now, models determine what our solutions are. So sometimes we use models just to predict. Sometimes we use models to find out what the optimal solution is, give us a solution. So that's called prescriptive model. And optimization is the process to determine. And we set up an objective function, and then it calculates an optimal solution. So let's look at an example. Maybe it'll make a little more sense. If we had a model that predicts unit sales at different prices, let's say unit sales is a function of 0.24 times the price. So once again, as the price goes up, our unit sales goes down, plus 3,000. Another model might be used to determine total revenue. So total revenue equals our price times our unit sales. Well, we could substitute in for unit sales and come up with our total revenue equals price times negative 0.25. This is just a substitute for unit sales. And then we could remember the old math, we could distribute, and we would get this function. And then we could optimize that function and the model would determine the right answer for us. Now, models can be either deterministic or stochastic. Deterministic just means all information is known or assumed to be known, and stochastic is where the information is uncertain. Last point I want to cover is sort of some steps to problem solving. So the first step is recognition of a problem. So that's usually there's some sort of gap between what's actually happening or your actual results and what you expected. The second is to define the problem. Now this is a very involved stage. Usually you want to get all the stakeholders involved, everybody that's influenced by the what's happening, because you don't want to put a solution in effect and then find out there's consequences you didn't think about. So involving all the stakeholders up front is very important. Then you want to structure the problem. All right, what's the goal? What does success look like? What are the constraints? Are there any constraints that we have or requirements that we have? Then the fourth step is analyzing the problem. And this is key for analytics because you want as much as possible in today's day and age to data-driven decisions. You want to get away from the gut feels if you can, or at least if you make a gut decision, you at least understand what the data is telling you. Number 5 is interpreting the results. And so models are rarely perfect. There's usually some sort of human intelligence. Where analytics is key, you want to know what that model's telling you. So you want to know if you do some human intelligence, how you tweak that. And the last one is implementing the solution. You want to make sure your stakeholders are bought in and that you've provided adequate resources and you've got some sort of monitoring stepped up. Well, that ends our chapter on our section on data. Hope this helps. Have a great day.